Consider the function f of x equals to sine squared kx over x squared, where x is not equal to 0 and k belongs to the positive integer subset. Show that the f is an even function, and given that the limit as x goes to 0 of f of x equals to 16, find the value of k. Okay, so for a, we have to remember that for an even function, our f of minus x is equal to f of x, as x is not 0. Okay? For an odd function, however, in case this pops up in your exam, f of minus x is equal to minus f of x. Okay? So since we have to show that f is an even function, we have to substitute minus x into our equation, where it would be sine squared k minus x is equal to minus x squared. Where here, since this is the same thing as sine k minus x squared, that still would equal to sine squared kx. It would still do that. Okay, and for minus x squared, the value would still be the same as x squared. We can prove this by just looking at, let's put in a value of minus 2. Minus 2 equals to 4, and the 2 squared also equals to 4. Okay? So on the top value, we would still have sine squared kx, and on the bottom part, we would still have x squared. So that is for question A. Part A, I mean, which is 2 marks, and it's pretty easy. You just have to remember the even function. For our next one, it would be a limit question. Okay, so for part B, we have the limits of x to 0 of f of x equals to 16. So our f of x is sine squared kx over x squared. And if we try to substitute 0, right, of this, sine squared k0 over 0 squared, this would equal to 0 over 0, right? Now this means that we have to use L'Hopital's rule, right? So L'Hopital, my pen is not working for some reason. Here, okay. L'Hopital's rule. L'Hopital's rule happens when you have a 0 over 0 or you have an infinity over infinity. Okay? So here, this would state that the limit of x as it goes to c of f of x over g of x is equal to limits of x to c f of dash of x over g of dash of x. So here, we just have to differentiate our top and bottom. Well, not here. We have to differentiate our f of x, g of x. So here we would have lim of x to 0. So ours would be here. Sine squared kx over x squared would be alright, so we can start with the product rule here, okay, to find ourselves our value of f of dash of x. So let me close this off real quick. Okay, so f of dash of x would equal to sine squared kx dx. So we are just taking the numerator here because we need to differentiate both the numerator and the denominator like separately. And this would ultimately be the same thing as sine kx times sine kx, which, as you can see, would be pretty good for a product rule. So now we apply our product rule here, where u equals to sine kx, u dash equals to k cos kx, and our v would equal to the same thing, sine kx. Our v dash equals to cos k cos kx. And here our dy dx would be u v dash plus v u dash. If you don't know what u dash or v dash is, it's practically the same as dy du or du dx, you know? And here would be sine kx multiplied with k cos kx, and it would practically be the same as this here as well, times k cos kx. Then we can just place them together, and it would be a 2 sine k, 2k, actually, 2k sine kx cos kx. And that would be our derivation for the numerator here. Our denominator derivation would just be x squared dx, which is the same as 2x. So if we look and place these values in here of our 2k sine kx, 2k sine kx cos kx over 2x. When we try to plug in our x value of 0 here inside here too, sine kx would equal to 0. Okay, so the numerator as a whole would be 0, and the denominator would also be 0. So that means we have to apply L'Hopital's rule again. Okay, so our limits as x goes to 0, and we start off again, but from this. So our derivation from 2k sine kx, sorry, my tablet wasn't working, kx dx. Here we can, of course, see that this can be applied with the product rule, so we can just start off with 2k sine kx here. Our u dash would be 2k squared cos kx. Our v would be cos kx, and the derivation of cos x is minus sine x, so this would be minus k sine kx. After that, we find our dy dx here, which is u v dash plus v u dash, which would be 2k sine k x times minus k sine kx plus cos kx multiplied with 2k squared cos kx. Now here we can simplify it. We can actually combine these k's together. So it would be minus 2k squared sine squared kx, because there are two sine kx's here, so that would be sine squared kx. And here we just multiply our cos kx together, which would be plus 2k squared cos squared kx. And we can just factor 2k squared out, so, which would be 2k squared cos squared kx minus sine it's squared kx. And that would be our numerator, 2k squared cos squared kx minus sine squared kx over 2, because our g dash of x would just be 2x dx, which would just be 2. And now when we input our 0 values here into our x's, cos squared kx, so it would be 2k squared cos squared 0 minus sine squared 0, because anything times 0 equals to 0, set these brackets, over 2. So that would mean that also cos 0 is equal to 1. Remember that? So it would be 1 minus 0 right here. So it would just cancel out. You would have 2k squared over 2. And now we can see that our limit of f of x as x goes to 0 equals 16. So from here we can just add this. Our limits of x as it goes to 0 of sine squared kx over x squared equals to 16 here. So here we just cancel it out. So k squared equals to 16, where k, we could just add this, equals to the root of 16, and which would mean that k is either plus 4 or minus 4. But this part would not be considered because we are only looking at the k values that are in the positive integer subset. So that's why we just have our k equals positive 4 right here.